Hi there! Today I'm going to be telling you about Load and Patch, improving hot patch capabilities in Curiosity's flight software. My name is Alexandra Holloway. I am the flight software team lead for the Mars Science Laboratory, and I'm here representing myself and my colleague Mark Maimone at JPL. Patching on Mars? Yep, that's a thing. NASA's Mars rovers have a history of lasting far beyond their designed lifetimes. But the longer they last, the harder it is to update their flight software. Challenges to long missions include diminishing testbed resources and personnel moving off project. As a result, we need more and more time to develop, test, and validate new full flight software changes. Hot patches are a great alternative. They can be developed and deployed relatively quickly, making them an attractive option for speedily repairing flight software when we need to. We've lost missions due to bad patching practices. For example, Viking 1. After years of operations, a flight software patch was written over code that we thought we no longer needed, some quaternion transformation code used during entry, descent, and landing. Unfortunately, that code was needed. It was used to control the high-gain antenna pointing, and once it was overwritten, the high-gain antenna could no longer be pointed correctly. And if we can't point the antenna, we can't talk to the spacecraft. If we can't talk to the spacecraft, end of mission. Another example is Mars Global Surveyor. Memory locations were modified as part of a software update 5 months before the mission was lost. But those addresses were specified directly as hex numbers, which turned out to be incorrect addresses. As a result, a later fault response executed the wrong behavior, and that led to the end of mission. Now we will use relative addressing. We'll use an offset from a known memory location instead of direct addressing, so that we don't do that again. A brief refresher of what a hot patch is. It's 3 easy steps. First, you load the image into RAM from non-volatile memory. This happens just as a part of boot. Code that is executing is stored in RAM, and that makes sense. Number 2, we load the modifications that we want to make to the RAM image. If the boot up is nominal, we load those modifications into RAM, and then number 3, we can apply those modifications from one place to another place, overwriting the image that's being executed. Every time you boot, you have to do all 3 of these steps. So it's not like you do it once and then you're good forever. No, you have to do this every time you boot. Is patching safe? Well, yes, with careful review, patching can be done safely. Unlike a full flight software update, hot patches do not modify the permanent flight software image. Hot patches are volatile. They must be applied after each boot up, and once the computer goes to sleep, they get wiped out. The primary overall safety mechanism is, should a problem occur that puts the vehicle into safe mode, hot patches will not be applied or executed. This means any problem introduced by a hot patch will be automatically removed while nominal functionality is restored. For example, the Spirit rovers Sol 18 multiple reboot scenario that occurred due to the flash file system problems cannot occur from hot patches. Viking 1's problem would have gone away after a single reboot if it had been implemented as a hot patch, which it wasn't. Impact on mission operations depends on how you implement the change. Here we've got a table of approaches, hot patch, macro or flight rule updates, component loads, and a whole new flight software version versus create time, test time, deploy time, and overall impact to mission ops. A hot patch is acceptable time to create the patch, acceptable time to test the patch, acceptable time to deploy the patch, and minimal impact. A macro or flight rule update takes about 3 to 4 days just also acceptable. To create it, 1 to 2 to test it. But deployment takes weeks, and the impact is large because it affects multiple tools and impacts every future tactical shift. Component loads, also we call those lukewarm patches. The create time is about 1 to 2 days, and that's a minimum. It'll take weeks of VSTB time on the hardware test bed for all of our regression testing that we might need to do. It'll take months to deploy, and the impact will be minimal, just like a hot patch. A new flight software version. We are currently working on a flight software version that's been in progress for about 5 years. So the create time is a very long time. Test time is a very long time. Deploy time could be years, and the impact to the mission is huge. So a hot patch is a reasonably low cost, low impact way to address an existing vulnerability in software. On MSL, we have used 13 hot patches in flight operations, where a patch consists of 1 or more individual memory modifications, sometimes with additional compiled code, and then also sometimes also a script that runs through those modifications in order. There were 27 ways of installing the 13 patches that we analyzed as part of this presentation, and there were 195 unique commands. And since hot patches are installed after each boot up, these 13 patches have been installed over 52,000 times. That's how frequently our hot patches are used. If you'd like more background, there's some links over on the right. Limitations of manual hot patching. First, let's look at the limitations of the VxWorks shell. It only allows you to write integers. Can't write floating point. There's no address verification. It doesn't care where you write, even if it's not word aligned. There's limited data verification, which results in a major effort to ensure that all of the writes that you expected to occur actually did occur. And then there's lots of steps to performing the patch, each of which are places where we could mess up. The first is you have to check the address for word alignment, then check the data at the address to make sure it's what you expect to see there. That means that you're not going to write somewhere you shouldn't be writing. 3, lift the write protection. 4, perform the write. 5, reapply the write protection. And then check the data again to make sure that the write succeeded. And with all of these places where we could mess up, we came up with load and patch. The goals of load and patch flight software are 4. First, we want to simplify complex programming in the high-risk task of flight software patching. Then we want to decrease coding errors for programmers. We want to provide better built-in error checking and allow for easier peer review due to slimmer programs. On the next slide, we're going to tell you how we're making that happen. We have created and exposed 3 write APIs and 2 read APIs from within the flight software. These new functions can update 32-bit integers, just like before, but also 32 and 64-bit floating point numbers, all in one line, and provide a return status, which you can then combine into one big status field using the return shift argument. That's the number of bits to left shift the return status value so that your calling script can OR together a whole bunch of these write functions. All updates perform both address and data verification, and they return status details, including any failure modes and their specific location. This ensures that all patch updates were correctly applied before continuing. All right, let's talk about load and patch errors. A helper ground tool automatically creates a VxWorks shell script, which collects error codes 3 bits at a time into U32 error status variables. Each variable holds up to 10 results. The ground tool also generates conditionals that check each error status value. That way, if any individual assignment, any individual poke fails, the error status will be non-zero, and the flight software will reject the hot patch. Humans can now disposition any problems using the error status value to understand exactly which memory assignments failed and why. And the why, there's 7 reasons, which are listed here on the right. Testing load and patch. MSL uses a multi-tiered test strategy to validate any of the software. Linux-based unit test certifies general functional behavior, provides code coverage numbers, and provides us with static analysis results. The next tier up from unit test is simulator testing. So we have a VxWorks VxSim simulator, which lets us do interactive testing and testing module interactions. Finally, we have flight hardware tests using the RAD 750 engineering models, running VxWorks and maintained to be as close to flight's hardware as possible. And this was especially important because all of these other methods make assumptions and abstractions that are just not true. Specifically, the VxSim has different endianness than the RAD 750 engineering model. So it was really important to get onto the hardware. In the end, hot patches provide a relatively fast mechanism to fixing simple flight software problems and can be fully achieved in a relatively short time during mission operations. Thoughtful design of supporting functions, such as load and patch, can greatly simplify hot patch development and review and provide more fault-tolerant installation and use. And this new capability is part of the new flight software for MSL called R13, and it's expected to be deployed to Mars mid-2022. Thank you for coming. My name is Alexandra Holloway from JPL, and this was a talk about load and patch. Thank you.